So what they're going to do is they're going to give us a derivative graph. They're going to give us a derivative graph, and they want us to tell, using the derivative graph, they want us to be able to tell you about the original. Okay? So given f prime, which is a derivative, we're going to have to find things like increasing, decreasing, relative maximum minimums, concave up, concave down, points of inflection, things like that. Okay? So like I said, so we're just looking at a bunch of graphs today, really just two graphs. Okay? Okay, so first thing to do is read the prompt. So I'm going to read the prompt and label some things that we can. So the function f is defined and differentiable on the closed interval from -6 to 6. That means there is a function who exists from -6 to 6, and it has derivatives. Okay. The graph of f prime, the derivative of f, consists of a semicircle, 3 line segments, as shown in the graph below. So the graph is not f. The graph is of the derivative of f. This represents the derivative of f. So this is the graph of f prime of x. Okay? So this is the graph of the derivatives. So this is a graph of all of the slopes of f. Okay? This represents all of the slopes of the original f. Okay? So when I say this dot here, so let me kind of give you an example. This dot here. This dot here is at 4, 2. That means in the original graph, which we don't have, when x equals 4, the slope is 2. It has a slope of 2. Okay? The original, when x equals 4, has a slope of 2. It means it's increasing. It means at 4, the original is increasing. Okay? Let me pick another point. Here. 0, 0. That means for the original, which we don't have, original, what I mean by f, when x equals 0, the slope is 0. What do we know about slopes that are 0? So if a slope is 0, what does that tell us? Horizontal tangents, right? When do we see horizontal tangents? Think of the last couple days, couple weeks, last week or so. When do we see horizontal tangents? When do we see the derivative equals 0? Maximums and minimums, right? Maximum and minimums. So that means everywhere along this line here is going to be a maximum and minimum. So anytime it crosses the x-axis, there's going to be a maximum and minimum. There. Those 3 guys right there. On the original had a maximum or minimum at -4, 0, when x equals -4, when x equals 0, and when x equals 6. Now, do I know if it's a maximum or minimum yet? No, I don't. But all I know is those 3 dots represent horizontal tangent lines. And the only time we have horizontal tangent lines, oops, no, I want to go that way. The only time we have horizontal tangent lines are at relative maximum minimums. Here, right? So we know that those represent maximum and minimums. We just don't know what. Okay. So let's go to the first question. Find the x-coordinate of each critical point for the original. I'm going to use a different color. Every time they say original, I'm going to use a different color. Now, we're not looking at the original. That's the important thing. We're not looking at the original. We're looking at a graph of its derivative. But on the original, where are they going to be critical points? So what are critical points? How do we know when we have a critical point or a critical value? When first derivative test, right? First derivative test. When the derivative switches from positive to negative, right? Positive to negative. If the first derivative is positive, it's increasing. If the first derivative is negative, it's decreasing. When the first derivative is 0, it's doing neither. So which of those are critical values? 1, 2, or 3? When are we going to get critical values? Yeah, so when it's constant, when it's equal to 0. So let's go back to our graph. Where are the critical values on this graph here? -4, 0, and 6. -4, 0, and 6. Because those we just said, those are where the slope is 0. The slope of the original. Those where the slope is 0. So we would say x equals 4, x equals 0, x equals 6. And then they're going to say justify your answer. Justify your answer means how do you know you're right? Because f prime of x equals 0. That's where this graph equals 0. This graph equals 0 everywhere along this line. When you say where does a graph equal 0? Everywhere along this line. Okay? All right, so let's go to the next one. Find the x-coordinate for each relative extrema on f of x from the interval -6 to +6. Label each as a maximum or minimum and justify your response. Do we know where the relative maximum and minimums are going to be? Yeah, we do. Right? Wherever the critical value is. Wherever the critical value is. Okay? What was the rule? How did we know? Let me use a better example. Let's use this one. How did we know that 0 was a relative maximum or minimum? How did we know that 4 was a relative maximum or minimum? The slope, the first derivative test, right? The first derivative was positive before and then negative afterwards. And then the opposite here, right? Okay. So we know something is a relative maximum when it was increasing. So when I say increasing, what does that tell me about the slope? The slope has to be what? Positive, right? So when the slope changes from positive to negative, that's going to be a relative maximum. Okay, so let's go back. I'm going to ask you a trick question. Where is the slope of the original? Positive. Where is the slope of the original positive? Where does it start being positive? Where does it end being positive? Think about it for a little bit. Where is the slope of the original positive? So let's start at the beginning. Is the slope of the original positive or negative? No. The slope of the derivative is negative. I'm going downhill, but is this the original? No, this is not the original. This is the derivative. I'm thinking of the original. So all of these dots, there's literally an infinite number of them, right? What do they all represent? What do they all represent? Let's write that down. What do all of these dots represent? The slopes of the original, right? So let's write that down. So all f prime of x So if I want to know about slopes for the original, I'm going to look here, right? I'm going to look at these y values. Right? So again, let me go back. Here, let me go back to this point here, the beginning point. That blue dot up there, that blue dot that I just made. This is at -6, 4. What does that tell me? In words, what does -6 and 4 mean? What does -6 and 4 mean? I know there's a dot there because I made a dot, but what does it mean in terms of what I'm trying to do? What does -6 mean? What does +4 mean? Pick another dot. Let's pick another dot. -5, 2. -2, -2. 2, 1. Any of those dots. What do any of those blue dots or red dots mean? What does the x value mean and what does the y value mean? So am I looking at the original or am I looking at, what am I looking at? What graph is this? What graph did we say this was? F prime, okay? So when I say -6, 4, the -6 is x, the 4 is y. Well, what does -6 represent? It just represents x, right? Just represents x. X is always just x. What is 4? 4 is the big guy. 4 is the important guy. What does 4 represent? The slope of the original. The slope of the original. So think of the original. At that dot there, was it increasing or decreasing? Increasing. Why was it increasing? Because the slope is positive. Because the slope is positive. At -5, 2, when x equals 5, what was the slope of the original? When x equals -5, what was the slope of the original? +2. Was it increasing or decreasing? Because it's positive. When does it stop being positive? That first red dot, right? So here, that represents a positive slope on the original. A lot of you look at that and you're like, that's negative. It's decreasing. Yeah, on the derivative, but I don't care about the derivative. The question didn't ask me about the derivative. The question asked me about the original. Where was the original increasing? Well, everywhere it's positive. Where else on the graph would it be positive? If we know this is positive, where else on the graph is positive? From where to where? 0 to 6. So let's draw that too. That's where f prime that's where f positive slope. That's where f had a positive slope, right? That's where f's slope was positive. Because all of those have positive y values. Okay. So what about underneath the x-axis? What type of y values do those guys have? Negative. So that means it's going to have a negative slope, right? Negative slope. Negative slope. So I'm going to erase some of these blue dots. So we don't need the blue dots anymore. The reds are all that we need. Okay. So let's go back to this one more time. Where does the original? The original. I'm not looking at the original. So don't look at this like you would a regular graph. This is a graph of the derivative. So where does the original change from increasing to decreasing? -4, right? -4. It changes from increasing, positive slope, to negative, decreasing, right? At -4, it changes from increasing to decreasing. So when something changes from increasing to decreasing, we call that a relative what? Not a minimum. If it changes from increasing to decreasing, it's actually a maximum. It's going to be a maximum. At x equals -4, we said, right? X equals -4. Justify your response. How do we know that? Because f prime changes from positive to negative. Changes signs. That's what led us to that red dot. It changes from positive to negative. Okay. Anywhere else on the graph, is it going to change from positive to negative? It looks like at 6, it's going to change, but do we know what happened after 6? No, we don't. So we can't say 6. It kind of looks like 6 is going to go down cross, but it doesn't quite cross. It just stops at here. So we can't say because we don't know. Okay? So let's do the opposite. Anywhere where we change from a negative slope to a positive slope. 0, right? 0. We change at 0. We call that a relative minimum. Because f prime of x changes from negative to positive. Okay. Okay. Let's go to letter C now. C is kind of in the mix, right? So where is f prime increasing and decreasing? This is the answer. I don't want to say I get this a lot, but this is the most common mistake answer. Oh, it starts increasing at -2, and then it goes up, and it's increasing until it gets to 4. Increasing, right? It's going uphill. Why is that wrong? That's f prime. Yeah, they didn't ask us about f prime. They didn't say when is f prime increasing or decreasing. They want to know when f is increasing or decreasing. So we have to look at it through a different lens. Okay, you're so used to looking at a graph and saying, when is it going uphill? Oh, from -2 to +4, right? That's if we're asking questions about the graph in front of us. They're not. They're asking questions about a graph that we don't have. Okay, so when is f prime, or sorry, when is f increasing? When the y values are positive. So anytime a y value is positive, it's increasing. Okay, so let's write that down. Increasing. Okay, so we have positive y values from -6 to -4. And then we have positive y values from 0 to 6. Okay, so let's write that down. Oops, from -6 to -4. And from 0 to 6. Positive y values. Positive y values on the derivative mean increasing on the original. Let me write that down. Positive y values on f prime are the same thing as increasing on f. And the opposite is also true. Negative y values on f prime equal decreasing on f of x. Okay, that's what we're looking for. So when do you look for an increasing or decreasing? Positive y values or negative y values. Okay. Okay, so decreasing. Negative y values start at -4 and go to 0. -4 to 0. We need to justify now. So how did we know that -6 to -4 was increasing? How did we know that 0 to 6 was also increasing? Positive y values, right? Positive y values. Positive y values mean this guy is positive, right? F of x, f prime is positive, yeah. Because f prime of x is positive. That's positive y values, right? Because the graph in front of us is the derivative. And the opposite is true. Because f prime of x is negative, less than 0. That's how we knew where to look. Okay. So now we go to points of inflection. Points of inflection. How do we find a point of inflection? I'm not even talking about the graph, just in general. In general, how did we ever find a point of inflection? Second derivative is when the second derivative is equal to 0. When the second derivative is equal to 0. F double prime equals 0. F double, that's going to be our justification. When F double prime equals 0. So we already did our justification already. We just got to go find it on the graph. Okay, so now we're not talking about F prime anymore. We're talking about F double prime. So what is the relationship between the graph I'm looking at and F double prime? F double prime is the derivative of this one, okay? So F double prime of x represents the slopes of F prime. The slopes. So now when I need to talk about F double prime, I'm not going to talk about the y values anymore. I'm going to talk about the slopes because that's F double prime. Okay. All right. So for example, let me use a color I haven't used yet. Green. Let me change this dot. That dot there, that green dot, light green dot I just made. If I'm talking about F double prime, I'm talking about the slope of that dot. So I'm looking at, so at -5, it's part of this guy here. Okay? The second derivative would be the slope of that segment. So the slope of this would be down 2 units over 1 unit, -2 over 1, which is -2, right? So the slope here, so a point on the second derivative would be -5 comma -2. That green dot, that's where that green dot would be. Because it has a negative slope, it's decreasing. Because I'm talking about the second derivative now. See what I mean? Okay. So here's not the hard question, but the big question. Where is F double prime going to equal 0? I'll give you a hint. There's 2 spots. There's 2 spots that F double prime will equal 0. Where will F double prime equal 0? Let me do this again. F double prime of this green dot. F double prime of this green dot here. That's at -5. To find the second derivative, I have to find the slope. So the slope of this segment was -2, right? So that means this green dot from -5, -2. Where will this y value be 0? Where on the graph will this have a y value of 0? That's what I'm asking. Where will it have a y value of 0? Not at 0. Close. Not -4. That's for the first derivative. Those are critical values for the first derivative. I'm looking for critical values for the second derivative. Where will this guy have a slope of 0? +4 is 1. Because it won't have a slope of 0, but it won't have a slope at all, right? This won't have a derivative. I can't do a derivative here because of a corner. It's a corner. So 4 works. Where else? There's one more spot. Not -6. -6 would have a slope same as -5. Where does this guy have a slope of 0? There you go, -2, right there. Right there and right there. -2 and 4. -2 and 4. Okay, that's where it has a slope of 0. So x equals -2, x equals +4. Because we always have a critical value where it changes sign. So I'm not going to use f double prime equals 0. I'm going to use this. I'm going to say f double prime changes signs. Okay. Okay, so go back to second derivative now. Where is it concave up and concave down? Well, if positive y values on the graph mean increasing and negative y values on the graph mean decreasing, where is it going to be concave up and concave down? We're not going to look at the y values. What are we going to look at instead? Slopes. Positive slope on f prime are going to equal concave up on the original. Negative slope on f prime of x equals concave down on the original. Okay? So that's what we're looking for. Where is it negative? Where is it positive? Where is a negative slope? Where is a positive slope? Let me erase all the stuff I have so I can. Okay. Where is a positive slope? Where is a negative slope? So let me start at the very beginning. Use a different color. Start at the very beginning. Positive slope or negative slope? Negative. Negative slope, and then I stop here, right? Because that was a critical value. And then I change, right? I go increasing, 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 stop there. That was a critical value. And then the last one is decreasing. decreasing. So decreasing from -6 to -2, decreasing negative slope means concave down. Increasing from -2 to 4, concave up. Okay. Okay, so concave up. Concave up, we said from -2 to 4. That's where it was increasing. -2 to 4. Because the second derivative was positive. The second derivative is positive. Concave down had 2 spots. From -6 to -2, and then 4 to 6. Okay. Okay, one more question on F, and then we're going to kind of sum up what we've done so far. Sum up what we've done. So we can tell where to look on the next graph, and the next graph, and the next graph. Because I'm telling you right now, you can mark it down. At least one of your FRQs will have a question just like this. Have a question just like this. Okay? Give you a graph of the derivative. Where is the original increasing? Where is it decreasing? Where is it concave up? Where is it concave down? Where are the relative maximum and minimums? Where are the points of inflection? Things like that, because they're extremely popular. Okay, last thing. If F, so on the original, we have a dot. On the original, we know that -2, 4 is a point on the original. Find the equation of the tangent line at x equals -2. Equation of the tangent line. Y minus y1 equals slope x minus x1. I need a point and I need a slope. What do I have? Do I have anything yet? I have a point. Don't I have a point? -2, 4, right? -2 is x, 4 is y. So how do I find the slope of the original at -2 using the graph? So I need to find the slope of the original at -2. How do I find the slope of the original at -2? Using the graph. You're going to use the graph. So here's -2. How do I find the slope of the original at -2? How do I use its derivative graph to find the slope of the original? The y values. Yep, the y values. Aren't the y values the derivatives, the slopes of the original? So what y value goes with -2? -2. That's the slope of the original. Done. That's the thing about this section. It's every time I teach this, I can see if you're really trying, I can see the kind of the steam coming out your ears because it's really a lot of thinking. You can't, there's, some of you I think wish just give me an equation and I'll find it, right? Just give me that and I'll find it, right? But when we're doing this, you guys are like, oh man, this is hard. It really isn't. This is where you real hard means you have to use your brain, right? Hard means you have to really think. That's when it's hard. That's what this is. Okay? Anytime you're looking at a table or a graph, you really have to use your brain because you can't fall back on an original equation. If I have the original equation, find the derivative. First derivative test, find the second derivative test. I can fall back on that, right? It's kind of a crutch. This you can't. You have something to fall back on, but you got to know how to read the graph, right? You got to know how to read the graph. And the graph is its own language. It's a different language than the equation. So you really have to. So there's two ways. There's two things that happen. Some of you are like, you know what? Let's do it. It's going to be hard, but I can do it. That's good because even though the first one was hard, the second one will be easier. The third one will be easier. The fourth one will be easier. By the time you're on the fifth one, you're like, oh, I got this. Right? That's what I want you to do. Kind of burst through that wall. Hit that wall. Right now, I know the first one, you kind of hit a wall and you're just like, it's hard to get through that wall, but you will get through it. Don't be the ones that just collapse at the wall because I already see that happening. I already see a few of you are just like hit the wall and you're just like, oh, I can't do it. Right? Don't do that. Don't do that. Okay? You're better than that. Okay? That happens a lot in this class. You're going to hit walls. You might need to hit it a couple times before you go through it, right? You're used to just hitting the wall once or not even hitting a wall, right? You guys in math 3, you guys just no walls. You guys just plowed right through them. But in this class, you might hit a wall. You got to hit it a couple times before you go through it. Okay? You can go through it, trust me. All right? Okay, so now this is probably the best part of the whole thing. It's going to show you where to look. When they give you a derivative graph, where do I look for these things? This is going to be kind of your Bible for this section because this is going to help you. Okay, so let's go over this. Last thing we're going to do. If I want to find critical points, where did I look? We did critical points, right? We did critical points. We did for question, I think it was A. For A, we found 3 critical points at -4 or 2, -4 and 0. Where did we look? Where did we look on the graph? Yes. So where f prime of x equals 0. So when the graph touches or passes through the x-axis. On the graph. Where it touches or passes through the x-axis on the graph. That's where the critical points are going to be. If we're looking at the derivative, you always look at, I'm not going to change it up and say, oh, here's the original. Now can you tell me things about, I'm not going to do that. It's always going to be the derivative graph you look at. Okay? Okay, so how did we know that relative maximum at -4 and relative minimum at 0? How did we know that? When the graph crosses the x-axis, right? So when it actually crosses the x-axis from positive y values to negative y values. So when it goes from positive y values to negative y values, that's a maximum. Minimum is the opposite. When the graph crosses the x-axis from negative y values to positive y values. Okay. Where on the graph did we look for increasing, decreasing? Where on the graph did we look for increasing, decreasing? Increasing positive y values, decreasing negative y values. So how do I say that? Positive y values mean above the x-axis. Yeah, above the x-axis. So is above the x-axis. Is below the x-axis. How do I find points of inflection? What did I look for points of inflection? Something about the slope, right? When the slope of the graph changes from positive to negative, or vice versa, from negative to positive. When the slope of the graph changes from increasing to decreasing, or the opposite, from decreasing to increasing. That's where you're going to have a point of inflection. Okay. When are we going to have concave up and concave down? Positive slope, increasing. Negative slope, decreasing. Let's see, slope of the graph is positive, aka increasing. Slope of the graph is negative, decreasing. Right? Where is the first derivative graph increasing? Where is its slope positive? Where is its slope negative? Decreasing. Last one will be done for today. And then on Monday, we'll come back to that. You're going to use these now that you kind of have a cheat sheet. This is your cheat sheet here. If I was a student taking the next test, this is probably what I would have on my note card. These things I would have on my note card, because you're going to have a graph. And I'm going to ask you questions like, where is it concave up? Where is it concave down? Where is it increasing? Where is it decreasing? If you don't know them by heart, that would be a good idea to put these things on there. Okay? So last thing, slope of the original. Slope of the original. That's the y value of the graph of f prime at the same x value. So whatever x value they give you, what is the y value on the derivative graph? And that's it. Okay? That's all the questions they're going to ask you. That's all the questions. So the next question is just the same questions. And then I'll give you guys different questions or different graphs. It's all about looking at different graphs and then looking for these things. It just takes practice, guys. It just takes practice. As long as you have these guys, you don't have any, you know where to look. Okay? Okay, so